All right, our next task is to run through a few more of these basic derivative rules. And on some of these, we'll talk through just sort of a basic idea as to why these rules are correct. I don't expect you to be able to do these verifications. I don't expect you to be able to reproduce them. But it is good for you to actually see these done so that it shows that we're not just pulling rabbits out of a hat, that these rules actually do follow from the definition of the derivative. So the first rule is this. Now we're going to combine this notation. So what I'm going to write is, for example, I will write the derivative of f of x this is just a notation. So I'm going to write in this, on the left-hand side, I will use this notation. On the right-hand side, I will use the prime notation. This is what the text uses. It's not the most common thing in the world, but it's straightforward, and if anyone who knows what you're doing understands this notation. So I will use this notation format. I will use the d by dx rule notation on the left. I will use the prime notation on the right. And so with that, we have the constant multiple. Or as we like to call it, the constant multiplier. The derivative with respect to x of k times the function. You'll notice that all of the examples we've worked through so far, there has not been a coefficient. I suppose in the strictest sense, the derivative of a constant doesn't really need a coefficient. But in all the power rule we've considered so far, there's not been a coefficient. Well, now we're going to cover that base. The derivative of a constant times a function, this can be any function, is given by the constant times the derivative of the function. Now, let me show you just a quick brush through as to why this is true. For your purposes, all you need to do is be able to know this rule and to apply it. So first, let's do this. Let's do a few specific examples of this. If we have, suppose f of x is given by 6x to the second. Well, this is a constant multiplier, and that's the power rule. So the constant multiplier rule says constant multipliers multiply along. Just like in limits, constant multipliers multiply along. Constant multipliers multiply along. And so with that rule, what this says is the derivative is 6 times just the derivative of that as if the 6 were not present. Well, the power rule says the derivative of that is 2x to the first. So this is times 2x to the first, and we can simplify that to give us 12x to the first. Now the net effect, let's do the net effect. This 12 is 6 times 2. So similarly, if I have 8 times x to the fourth, then g prime of x is given by 8 times the derivative of that is 4x to the third, but 8 times 4 is 32. And so the net effect is this coefficient is the coefficient multiplied by the exponent. So from this point forward, I will allow you to skip this step and go directly to the final result. Not only will I allow it, I'll kind of pretty much expect you to be able to do this. And so if we have h of x is given by, let's say, 10x to the third, then we can go directly to h prime of x, the final result. Multiply 3 times 10 is 30, x to the second. Similarly, if f of x is given by the square root of x, let's go 5 square root of x. Well, we can rewrite that. First, there's no calculus happening here. This is just rewriting. This is rewrite. F of x is given by 5x to the 1/2. And then our sort of extended power rule says multiply by the coefficient. So the derivative, 5 times 1/2 is 5/2. X raised to the 1/2 minus 1. That's 1/2 minus 2/2 is negative 1/2. And that's our derivative. And so the constant multipliers multiply along. Let me do a quick little brush through as to why this is true. Again, you do not need to be able to reproduce this. I'll write this in this blue color. You do not need to be able to reproduce this, but I'm going to show you where it comes from. the derivative with respect to x of k times f of x, well, by the definition, that's the limit as delta x goes to 0 of k times f of x plus delta x minus k times f of x all over delta x. It's just there's this constant multiplier every time you write down f of x. But this k can factor. I can factor this k, so this is delta x. Sorry, limit as delta x goes to 0. Factor out the k, and that's f of x plus delta x minus f of x all over delta x. But this is a limit of a constant times the expression. We already have the property that in limits, constant multipliers multiply along. And so we are permitted to move this constant multiplier in front of this limit. And what we're left with is the limit, delta x goes to 0, f of x plus delta x minus f of x all over delta x. But what is this? That expression is f prime of x. That's k times f prime of x, and that's our statement. The derivative of a constant times the function is the constant times the derivative of the function. And so the reason constant multipliers multiply along for derivatives is because constant multipliers multiply along for limits. And so we say this property for the derivatives, we say this is an inherited property. The constant multiplier property for derivatives is inherited from the constant multiplier properties for the limits. In any event, constant multipliers multiply along for derivatives. Now, our next actual rule is the sum and difference. You'll notice that all the examples we've done so far have been a single term. All the examples we've done so far have been things like 4x to the second. We have not yet considered how to work something like 5x to the third minus 4x to the second plus 6x minus 8. We've not yet considered how to find the derivative of a string of these added or subtracted from each other, and that's what's up next. It says the derivative of f of x plus g of x is given by the derivative. This is the derivative of the sum. The derivative of the sum. It's the derivative of the first plus the derivative of the second. The derivative of the sum is the sum of the derivatives. And the proof of this follows exactly a similar pattern to this. You form this large difference quotient, and then you separate the difference quotient from itself, and you get these little pieces. And so this is a very straightforward demonstration. Actually, the text has a nice demonstration of it. And what this says is the net effect is if you have the derivative of things added together, and it turns out it also works if you subtract. So if you have plus or minus, plus goes to plus, minus goes to minus. The derivative of the sum or difference is the sum or difference of the derivatives. So what this means is you just go term by term by term by term. Derivative here, minus derivative here, minus derivative here, minus derivative there. And so in this case, the derivative of g is 15x to the second, that takes care of this term, minus 8x to the first, I'm going to put the first just to emphasize, plus, now the derivative of 6x, let's recall, let's be very cautious here, the derivative of 6x, remember this is 6x to the first, and the power rule says 6 times 1 is 6, times x raised to the 1 minus 1 is 0. I'm going to leave that there just for now. And then, we already know the derivative of a constant. The derivative of a constant is 0. And so now if we want to rewrite this to make it look a little nicer, this is 15x to the second. We can leave off this x to the first. And x to the 0 power is 1. Right? X to the 0 power is 1. And so this is plus 6. Let me take a look at this a little bit more closely. the derivative with respect to x of k times x to the first. This is a linear, right? X to the first is linear. Remember, this is x to the first. It's just a special case, as we've done here, of the power rule. So the derivative of k times x is exponent, which is 1 times k, and then x raised to the 1 minus 1 is 0. So officially it would look like this. If you want to put in all the little details, that's what you would have. Multiply by the 1, then we have 1 minus 1. But the net effect is k times 1 is k, and x to the 0 falls out. And so the overall net effect is this. The derivative of a linear term is the coefficient. The derivative of a linear term is the coefficient. The derivative of a linear term is the coefficient, and we don't need to go through that way station every time we work this problem. So, again, more basic rules. There's the constant multiplier, multiplies along, and then we have the sum and difference. We'll get to a few more rules in a bit. The next video we're going to talk about is ramps up the discussion a little bit, because our next video is going to concern ourselves with this. What happens when we throw in the trigonometry? What is the derivative of sine? And what is the derivative of cosine? And we'll consider those in our next video up.